Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept, and if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more.
Hello students, very good morning to all of you. Welcome back to my class on Physics 1. It has been a long journey. Now we have taken 9 classes. In those 9 classes we covered variety of topics. I told you in these first year courses we study variety of topic, and most promising of them maybe the quantum mechanics one. Now the quantum mechanics one talks about the most modern physics, and we are learning quantum mechanics in 2 steps. In as a matter of fact, the quantum mechanics one discusses mainly on the theoretical aspects. It discusses many variety of theoretical issues. I told you we'll be studying a lot of experiments starting from 1900 to 1927, and each experiment is expected to give us a new insight, and which it has been doing so also. We started our journey with Planck's explanation of blackbody radiation. Then we studied photoelectric effect, Compton effect. Now each experiment, if you look back, they have been giving us some wonderful concepts. Okay, so far we developed 2 important concepts. One is obviously the concept of wave particle duality, that is coming as an immediate conclusion of the photoelectric effect and Compton effect. And last day, actually, if you follow my last video lecture, I ended up with a reverse concept of what Compton is doing and what Einstein is explaining in photoelectric effect. Okay, that they are telling that a known wave can be matter-like. Reverse concept is that I shared a matter can be wave-like, and that was predicted by a scientist, Louis de Broglie. So I ended my discussion of the previous video lecture with by the name of de Broglie. So today, but the major objective of this session is to talk about the hypothesis or the idea that is shared by de Broglie. Mind it, what de Broglie is telling, it is an hypothesis. Hypothesis means it's a proposal. And what we did with Compton effect and photoelectric effect and concluding the wave particle duality, those lines, that a wave can be matter-like. Okay, that those ideas are conclusion of some experiments. So what de Broglie is telling, so now is just an idea. We have to substantiate that with some experiments. Okay, so that is a long journey. So the major objective of today's class is to basically to introduce de Broglie in front of you. We will talk about his hypothesis. We have to discuss where it is applicable, where it is less applicable, or in general what is there waiting for you. So after attending this class, you'll be able to explore obviously the exhibition of wavy nature by a matter. For which type of matter is more it is more observable, for which type of matter it is more measurable. So all these issues we discussed. So it's a wonderful journey waiting today for you. So let us begin the journey. Okay, so now obviously this is the 10th class in a row, and this is myself. You can see, you can always contact me through those email IDs, and there is also my WhatsApp number. Okay, and every day at the beginning I'll remind you about Max Planck, because with him we actually started the journey of the quantum world. Okay, because Planck explained this very beautiful experiment of black body radiation. As all of you know, he explained black body radiation quite wonderfully. Okay, that experimental curve of black body radiation was obtained, and integration like that is expected to give the total energy, but Planck actually explained that we did not have the right expression of E lambda. Planck has given that right expression of E lambda with the formula, with an hypothesis that energy of an object could be discrete. Okay, so this discretization of energy concept. So because of the Planck's that idea, it was a novel idea, new idea, unique idea at that time of the physics, that somebody is thinking beyond the box, that energy of an object could be discrete. So at that point, actually, physics is divided into two parts: classical and modern. Classical means the physics, where you define that matters are there, something, waves are something. You define a matter like with mass, momentum, size, and shape. When you learn mechanics, you basically talk about matters, and the waves are like light and sound. So when you define wave with some other feature, okay, like wavelength, frequency, and phase. So my main intention of this journey is to show how this departure is taking place in your classical sense. So this is what about wave, this thing, okay. And so what will happen is that I told you, I reminded you that best exhibition of material nature is obviously the collision, okay, and the best exhibition of wave nature is obviously the superposition. Only waves can superpose, okay. Only waves can superpose. Superposition is exclusively a wave property, and wave on a matter makes scattering. That I also told you. The classical reflection is a scattering process. So this is the classical viewpoint. These are the three things that can happen in nature. Now these are all departed. We have actually deviation takes place in this classical concept. When you studied photoelectricity and Compton effect, both the experiments have been well discussed in your class. And so photoelectricity, it tells you that classically it appears to be a wave on a matter. It should be a scattering phenomena, but ultimately it was a collision phenomena between electron and photon. So it was a new concept. Einstein introduced the concept of photons. Photons were making collision, and with the idea of photon-electron collision, it was all explained. This was a picture which is known to you now. Photons are like matter. It is that they are having some momentum, some mass. They are colliding with another matter electron. So because of that collision, electron takes up the energy from the photon and ultimately goes out of the metal. So after that, Compton came into business. So we studied the experiment of Compton effect, okay, which is also photoelectricity is proving that it's an experiment where it shows a non-wave light, because photoelectricity was done with ordinary visible light, okay, showing the property of matter, photons who are colliding. So this was further established through the experiment of Compton effect. Now, what Compton effect did, okay, in that experiment, okay, it was done with X-rays, and in this experiment, what was happening? The X-ray photons or X-rays were coming in, X-rays were getting scattered by elements like carbon. So initially, we thought, like normals, it is like usual scattering, which is shown again on the picture there, but the peculiarity here is the change in the wavelength. The scattered beam was coming out with a modified wavelength. So today we know how Compton explained it. Compton explained the whole situation with photons concept. That is, the photons coming in, and the photons are making collision, elastic collision with the electron. Okay, so because of that collision mechanism, he actually estimated everything: photonic mass, photonic momentum. So ultimately, he could define photon also. It's a matter of some energy, some mass, some very insignificant mass, h nu by c square, if h nu is the energy and h nu by c is the momentum. So ultimately, so what would happen? You notice there that the explanation was given by Compton, that it's photons are like matters, they're making collision with electron. Because of collision, photon loses energy, so its wavelength changes, modified, and electron takes up energy and moves away. So again, it's a departure from classical concept, because in this experiment you are not thinking X-ray as a wave, you are thinking X-ray as a stream of matter photons. What photons are doing? They are colliding. Who collides? Matter collides. So it is exhibiting that feature. So ultimately, all these things were discussed in your class. This change in wavelength was calculated from the basic theory of elastic collision. From the basic theory of elastic collision, it was done. So ultimately, today, if you look at summary of the photoelectric effect and Compton effect, both of them are talking the same. They are actually in the same tune. They are doing the same thing. They are telling the same thing. What they are telling? There are at least two experiments in nature which are showing that a wave can be matter-like. light can be photon-like. Photons are having properties like momentum. Photons are making collision with electron. Who collides? Matter collides. So in my class, when I am teaching you the Compton effect and photoelectric effect, I told you radiation is behaving like photons. On the contrary, when you attend your physics practical classes, when you do laser diffraction, same photon or the same light, okay, there you have to operate with a red laser light, okay, laser. So there you describe that entire phenomena as a diffraction experiment, diffraction through grating. So light gets diffracted, after that interferes, gives those wonderful patterns that you have seen those in your inside your lab. So basically, in that experiment, how it is behaving, the radiation in the physics lab, it is behaving like waves, because you have seen those spots, you have seen those red spot in the experiment of laser diffraction. So those spots have got variable intensity. So intensity was redistributed. In nature, intensity can be redistributed if there is interference. Interference means superposition of waves. Who superposes? Waves superposes. So if you have to explain those spots in the laboratory, in the physics lab, you have to use the idea of interference. And interference is exclusively a wave property. So in the physics lab, you have to consider light as a wave. And I told you in my class, when I am teaching you photoelectric effect and Compton effect, you are thinking light as a stream of matter, photon. Photons are having properties like momentum. They are making collision with electrons, which are essentially material property. So there was a big question mark. What electromagnetic wave is? What light wave actually is? Or electromagnetic actually is? Is it a matter? Is it photon? Or is it a wave? The answer is that it is both. Okay, even light does not know what it is. The answer is that it is both. Or in other words, it has got a dual character, dual nature. In some of the experiment, it is like photons, like Compton effect and photoelectric effect, and in some other experiments, it is like waves, like interference diffraction. Problem is that you cannot use my photonic theory in your physics lab in the interference experiment, and you cannot use your wave theory in my Compton effect, because there, if you consider this X-ray as a wave, then you cannot explain the change in lambda, because in normal scattering, then it becomes a scattering experiment, and in normal scattering, wavelength does not vary. If I send red light on the wall, it does not become orange, or it does not change the color. So with your scattering theory, just like the way you cannot use explain by Compton effect, that means you cannot use wave theory in Compton effect class. Similarly, you cannot use photonic theory in your interference class. So basically, it has got a dual character. But the only condition is that whenever it is showing photonic nature, don't use wave concept. And whenever it is showing wave in nature, don't use photon concept. So this is called wave particle duality in quantum mechanics. Okay. Now after that, actually, you can sorry. After that, you can see the whole situation. That therefore, photoelectricity or Compton effect, both of them tells you the single line. It's a story of betrayal, that it's same light wave, same electromagnetic wave is showing not the property of wave, showing you the property of matter. So that is the main message coming from both the experiments. I told you at the beginning, each experiment is going to give you a lesson. What is the lesson from this? Lesson is that at least there exists two experiments in nature where electromagnetic radiation is not showing wave in nature, showing the property of matter. Now, after that, if you could recall, I did a bit of small calculations. What is that calculation? Calculation is, suppose I ask you to dream a bit, okay? So this is a statement of wave particle duality, which you know from my previous discussion. That is a statement of wave particle duality. Whatever I told you, it is manifested there. Okay. So this is what is meant by wave particle duality. Electromagnetic wave, both wavy feature and photonic feature, but it cannot show both the nature together. Okay. Now you can see the same picture. Now I ask you to dream a bit, okay? You see, what is a dreaming? Suppose from childhood you know there is nothing like light. It is nothing like wavy nature of radiation. It is all photonic nature. You only know about photon, just like you know say electron. You only if I say electron, you always regard it as a matter. You define it with some mass, say 9.3 10 to the power minus 31 kg, some charge. If it moves, you get a current. So at the back of your mind, you always regard it as a matter. Similarly, suppose if from the childhood you know electromagnetic radiation means photons, stream of photons. So at the back of your mind, you are thinking it as a matter because photon is defined with its own momentum, h nu by c. So now I ask you to look at that equation. You can write down this equation in that form. H nu by c you can write down in this way. C by nu. C by nu according to the basic electromagnetic theory is like lambda. So what it gives a formula lambda is equal to h by p. Now what is the meaning of lambda? Lambda indicates, okay, photon is a matter with this momentum h nu by c. If the matter photon shows wave nature, then it should have a wavelength, and that wavelength is given by h by p. Okay, it's a very funny equation. There, here by this equation, two different features are connected with together. Before 1900, people thought waves are different, matters are different. Now, what this equation is doing is this equation is a bridge between those two concepts. Earlier, people thought for matters I have got mechanics, for waves I have got wave theory. For matter, my variables are mass, momentum, etc. For wave, my variables are wavelength, frequency, and phase, etc. Now, what this small little calculation is doing, it is breaking many jinx. It is telling that a photon is a matter, but if the photon shows wave nature, that is the usual light that you know, it should have a wavelength, and that is given by h by p. So if you look at the equation, left hand side of the equation is a wavy nature, and right hand side of the equation is a particle nature or material nature. So I've got a bridge between the two worlds of waves and matter. It's a very funny equation, and it is coming as an immediate consequence of if I just change my view a bit. Suppose I only know photons, and suppose I am thinking about if just by mathematical manipulation, if a photon can show wave nature, it should have a wavelength like this. Now this gives some hints to another aspect. What is the hint? That if a photon can show wave nature, it is defined by some wavelength lambda is equal to h by p. That means what is photon? Photon is a piece of light or material property of the so-called electromagnetic wave. Now I can generalize this concept for any matter. Any matter therefore can show wave nature. Any matter moving with some momentum p therefore can show wave nature, and if it shows wave nature, its wavelength should be h by p. Now this is not my idea. This idea was actually conceptualized by a scientist, Louis de Broglie. Louis de Broglie actually utilized this idea. If you look at this entire description, the way I'm presenting in front of you is this much. You know this much. Say a wave can be matter-like. Now what de Broglie is telling, opposite should be true. Just like the way I have shown you with calculation, a matter can be wave-like also. Okay, and that way, this is the idea of de Broglie. Matter can be wave-like. Okay, de Broglie is telling a matter can show the property of the wave. So it's a, and if it shows wave nature, its wavelength should be h by p. That thing you know. So now today we'll try to know what de Broglie actually told. So hypothesis of de Broglie. Okay, the other side of the story. You see, it makes the cycle complete. Wave particle duality tells you waves can be matter-like, and de Broglie is telling the matter can be wave-like. And that is our entire universe. It is we, the human being, who are thinking sometimes mechanics for matter, wave, so sometimes something as matter, something as wave, like that. What it appears now, the same thing can sometimes show the property of wave, same thing can sometimes show the property of matter. Light is wave-like in interference experiment, and it is photon-like in your Compton effect experiment. Electron is photon matter-like in Compton effect experiment, and it may be wave-like in some other experiment. That is the meaning of this entire discussion. That a matter can show wave nature, a wave can show material nature, that you know, because you studied photoelectric effect and Compton effect, and you know a particle duality concept. Now, if you generalize that concept, you get this very wonderful idea. Matter can show wave nature. Electron, which has been colliding in Compton effect, can show the wave nature, and that is what de Broglie is telling. This is called de Broglie hypothesis. Okay, hypothesis of de Broglie. So that means this picture. Okay, same thing. Whatever I told you. Okay, matter can be wave-like, and its wavelength should be h by p. Now, de Broglie hypothesis is like this much. I told you already. Any matter moving, any moving particle, as a matter of fact, can show wave nature. But again, there is a caution: when it is showing wave nature, don't use the particle concept, and when it is showing particle nature, don't use the wave concept. Okay, or vice versa. Okay, understand? So now this is the statement of the, as I mentioned. Okay, now let us just extend the idea a bit. Suppose an electron is moving along, suppose along that arrowhead. Let's consider that to be positive x. Its mass is m, velocity v, momentum p. Classically, we know that if I've got a second electron here, these two electrons will collide with each other. That is an exhibition of particle nature. Now, the point is that I want to clarify. In my class, I do not want to discuss that, because how two matters collide, that you know from classical physics. My class begins with the Broglie. Okay, that is, see the same electron shows the, you see the same electron, not the matter electron, it is showing the property of wave. Okay, then my class begins. That wave is called the Broglie. That idea of the wavelength is also given by the Broglie formula as h by p. So I am with electron, but to me electron is not like a matter electron, it is showing the property of the wave. Okay, so this is the same thing in coming in different way. So these are the waves of electron. Okay, but how these are coming out? Question is that if electron is a wave, then these are waves of electron. How this concept of wave of electron coming out? Or what I am actually telling? Okay, or how all these words are physically meaningful, that I am telling that a matter can show wave nature. Suppose a train is moving, can it show wave property? Or if it shows wave nature, what kind of wave it is? Okay, so many open questions are there. That is, the Broglie is telling a matter can show wave nature, but how far it is applicable, or what kind of wave the Broglie is talking about. Or another important is the issue is that, is there any experimental validity of this idea? All these things need to be clarified. All these things need to be reiterated. You see, I presented on the screen waves of electron. I hope you don't understand anything by this wave. I have to illustrate it. What does it mean? Because you can see some beautiful pictures up there, but you have to realize it. Okay. So I've got an electron moving along x direction. Let m be the mass of the electron. Let v be the velocity, or u be the velocity of the electron. So the momentum of the electron should be mass into speed moving along this direction. Now the idea is that if in this journey, if this faces another electron, so what is expected from classical physics? If this, suppose this electron is a static condition, so after some time they will impinge on each other. So the first electron will go to this position, second electron is static already. So first electron will move, and it is expected it will hit it. Okay, they will collide. So my point is that you have got no interest on this issue, because you know this from your classical physics. My class begins if this electron follows the idea of the Broglie, if they show the property of okay, if it follows the Broglie idea. But still open question is that what is this wave is? Okay, we'll discuss it. Okay, but you have to wait a bit for that. So now what would happen? So what is the message that is obtained from the Broglie? That if I've got an electron moving along x direction, as is mentioned, it is mass is m, velocity u, moving with some momentum mu in this direction. And the idea is that if it electron shows the property of wave, I am not telling electron is a wave, I am telling it has a chance to show the property of wave. Like best exhibition of wave nature is interference. Okay, if it could shows the property of wave, then it should have some wavelength. Then its wavelength would be lambda is equal to Planck constant by mass into velocity, which I calculated for photon. We just discussed it for a photon few minutes back. That is a generalization of idea. Lambda is known as the de Broglie wavelength. So now we'll do de Broglie wavelength calculation. I did it for photon initially in your class in the presentation. Now let me take two examples, two arbitrary problems for the calculation of de Broglie wavelength. The first, I will take up two examples. One is a moving car. Suppose a train is moving. Now the mass of the train, say maybe 60,000 kg or even more it can be. And it is moving with a velocity, suppose it's a high speed train, 120 kilometer per hour. Suppose this is x direction. Okay. Suppose that is x direction. So train is moving. Now suppose, so if you do it in meter per second, it is 120 into in kilometer means 1000 meter by 3600 meter per second. So zeros do cancel, and you can understand it will be like this much. This is 1000. Okay. So two zeros cancel. So 36 into 120 is close to 3. So it is like close to 30 meter per second. So this will be the speed of the car train in meter per second. Now suppose the train is moving and it is following the Broglie. If it is following the Broglie hypothesis, its wavelength should be h by mass into velocity. That is 6.62 10 to the power minus 34. Okay, mass is 60,000, 60 into 10 to the power 3, and speed is 30 meter. So if you calculate it, it is like 6.62 by 6 is nearly 1. 10 to the power minus 34 in the denominator, 10 to the power 3 into 10 to the power 4. So 6 by 62 is nearly 1. 1/3 is basically 0.3, and 34, and this will be of the order of 10 to the power minus 13 meter, 39 meter. So the Broglie wavelength is very small. So mathematically speaking, it is too small. And you see, you can go up to the dimension of atoms. The atomic dimension is of the order of 10 to the power minus 13 meter. But this is too small a wavelength, very small, too small a wavelength. So even if, so this is, we don't have the instrument to detect it, can't detect it. We don't have the instrument to measure it, okay, because the wavelength is too small a wavelength. So what we can do now, we can now compare. Obviously you will get some more practical reason in the latter part of the discussion, that it is meaningless to discuss about the wavelength of the matter for large object, okay, in any case. Okay, so now let me give you the example of another object, that is a electron. If I consider one electron, suppose it is orbiting around the nucleus with the orbital speed is very high, 10 to the power 7 meter per second, and mass of the electron, non-relativistic mass is like 9.3 10 to the power minus 31 kg. Now if I consider the wave nature of the matter electron and try to calculate its de Broglie wavelength, again this is mass into velocity, 6.62 into 10 to the power minus 34. Mass is like 9.31 into 10 to the power minus 31, and speed is like 10 to the power 7. So if we do it, 34, this is like 34 and 31 minus 3, it is of the order of 10 to the power minus 12 meter. And this is, as I mentioned, atomic dimension is of the order of 10 to the power minus 13 meter. Okay, so if this is reachable. Okay, this is reachable. You can go up to this dimension. So obviously, this is also reachable. Okay. So if a matter shows wave nature, like electron, like matter shows wave nature, so this is detectable. Theoretically, for large object it is possible, but practically that is meaningless because such a small wavelength. Okay. So that means the wave nature of matter is exhibition of wave nature of matter is, if we consider electron, it is much larger compared to the large object that I consider. It is of the order of 10 to the power minus 12 meter, and it is minus 10 to the power minus 39 meter. So this is more detectable in actual experiment. Okay, the wave nature of matter electron is more detectable in an actual, you can measure it in an experiment actually. So that's why in all your chemistry books, when you see say electrons orbiting around the nucleus, you have been introduced the idea of electron cloud. But so that means I'm talking about the wave nature of electron. But the question is that what kind of wave it is, because it's a very special kind of wave. It's a wave of probabilities. Okay, so that question you have to mention. Okay. Now, one pertinent question that often comes in examination, and I will also show you, that is the Broglie wavelength calculation. Suppose an electron is moving, mass m, velocity u, momentum mu. Now it is subjected to a voltage. Okay, it is moving through an electric field. Some voltage is applied. Okay, some voltage V is applied. External voltage. So if you apply an external voltage, then kinetic energy of the electron will be half mu square if the electronic charge is E into V. So from here on you can write down U is equal to 2 eV by m square rooted, or the momentum of the electron will become is equal to T, the momentum will now become equal to root over 2 mev. So express the momentum of the electron in terms of the applied voltage. Now suppose you wish to measure the de Broglie wavelength. So de Broglie wavelength now will be equal to h by momentum, h by over 2 mass into velocity. Okay, 2 Okay. So sometimes some questions do come in like this. Okay. Suppose we apply a voltage say 50 volt. Then what would be the de Broglie wavelength of the electron? It is 6.62 into 10 to the power minus 34. Twice mass is 9.3, 10 to the power minus 31 kg. E is like 1.60 to 10 to the power minus 19. Applied voltage is like 450 volt. If you apply, put it, you can calculate the electron wavelength. Okay, so these are another type of problem. So these are variety of problem we'll be calculating in particularly one experiment also you'll get to know. So with this in mind, let me get back to the PPT a bit. These are some more problem of de Broglie wavelength calculation, a similar problem. Okay, 2 mega electron volt is where it has been calculated. Now to open question is there. Okay, find what de Broglie is telling. I am accepting that electron has got a that there is a chance that a matter like electron can show wave nature. Okay, uh, electron can show wave nature. Okay, if it shows wave nature, it should have some wavelength, deep wavelength, that is h by mass into velocity, or if it passes through a voltage, h by root over 2 eV. So all these things we came to know now, but the question is that these are all hypotheses, these are all theory, these are experiment to prove it. And what I have not told you, I am talking about wave of electron, wave of electron. Is electric, what kind of wave it is? Because by wave I know I light and sound. Okay, electromagnetic wave and acoustic. What kind of wave it is? Okay. So first answer is there, experimental proof is there within 3 years of the Bragg idea. It was proved by Davison and Germer in 1927, the wave nature of the matter electron, and experiment was done for electron diffraction experiment. But one thing is not clear till now. You see this picture, these are electron waves. Okay, so a P wave, D wave, we have learned that. But what is that wave? Is the electron becoming wave? Answer is no. Electron is not a wave. Electron is your favorite matter electron. But it's a wave of what? Who makes this wave? For example, light wave is made by electric field and magnetic field vibration. Sound wave is vibration, is a mechanical vibration. Who makes this wave of electron? What kind of wave it is? It is not electron, but it is the wavy feature of electron. What is this? So wait for that. Okay, in the next class I will discuss this. Okay, because that is something new. I am talking about electron showing wave nature, but at the same time, I'm telling electron is not a wave, but electron can show the property of wave. And whatever I am showing you, these are the wavy nature of the electron, but it is not electron. It's a fallacy, no? I'm creating it's fallacy within my words. I'm saying that electron can show wave nature, but the pictures I'm showing, I'm telling these are not electron waves. This is not electron, but this is the wavy nature of electron. But any wave is a vibration of something. Something has to vary to make that wave. Who is making that wave? That question needs to be answered. Then the question of the further understanding. So in the next class, we'll try to realize that. Thank you for the time being. We'll discuss this very important issue in the next day. Bye.
You and me were meant to be in the great outdoors, forever free. You and me meant to be in the great outdoors, forever free. Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together, it's so beautiful. You and me, we meant to be in the great outdoors, forever free. Sometimes you need to go and take a step back to see the truth around you. From a distance you can tell